Well, thanks for that introduction. It's very kind of you to have me at PLNOG. Dzień dobry. My name is Pim Van Pelt. I'm Dutch, but I live in Switzerland. And today I have a talk lasting about 35 minutes that talks about a rather popular, very quick data plane called vector packet processing, and compares it a little bit to how the kernel might do routing. So it's actually three pieces in this talk. First, DPDK and VPP, the stuff that makes this data plane so very fast. Then some code that I wrote and contributed to VPP that allows us to use things like BGP, OSPF, and other control plane software on top of it. Then we talk about load testing to just prove that this stuff is actually really, really fast. And then especially for PLNOG today, I have some screenshots and sort of configuration snippets that show some L2 and L3 features that I think are really, really cool in VPP. So here we go. I've been a member of the RIPE community since about 1999, so have the Dutch domain ipng.nl for about 23 years. I moved to Switzerland 16 years ago. I had to get the obligatory Swiss ipng.ch, and in the pandemic I got bored, founded a company, incorporated, and built a small ISP based on the work that I've been doing in the open source before. So Ibmg Networks GmbH is a limited liability company in Zurich. I live in Brüssel, that's where I'm calling you from now. As we're a tiny operator, nobody knows us, don't worry about it. Nobody knows us in Switzerland either. We're not very large, but we do run VPP and DPDK fully open source routers that give most silicon-based routers a run for their money, really. And the map you see here is around the small town of Brüssel and a little bit of Zurich, a larger town in Switzerland. But we also built a European ring that goes from Zurich to Frankfurt and Amsterdam, and then the north of France and Lille, Paris and Geneva, and then back to Zurich as well. And on these nodes, we run VPP with Bird as a routing suite. We peer on most European internet exchanges that are around this ring. People call that peering on the flap. In my case, I'm also peering on the flap, except it is Frankfurt, Lille, Amsterdam, and Paris, with about 1,800 or so adjacencies. It puts us at the top 5 of well-connected Swiss ISPs in Europe. We run ASA298. We got that from 6Access. You may, if you've been around for a while, remember this was an IPv6 tunnel broker that I started in 1999, and I've run through 2017. AS number was up for grabs, so I took it and now have 4-digit AS to humble brag about. So the talk today is a juxtaposition between how Linux or FreeBSD or OpenBSD might do kernel-based routing. And I'll first start by kind of explaining how clumsy it is for a general purpose thing like the Linux kernel to do. Like typically when you get a packet or maybe a bunch of packets with interrupt coalescing, your network card will issue an interrupt to the kernel. The kernel stops what it was doing. It was playing YouTube videos or something. And it has to go handle this packet. And it goes through a linear flow by looking up what type of packet this was, and was this maybe an ARP or IPv4, IPv6, or maybe MPLS, packets. Then it has to figure out, is this thing destined to me? Is it to be handled by the local TCP/IP stack? If so, hand it off, to the TCP/IP stack, or should I route it? In which case, we should look up where to route it to, decrement TTL, perform NAT, like filtering, all that stuff. And eventually, we know what interface to send it out to, if to do a layer 2 lookup, like which MAC address to send this to, rewrite that L2 header to have the new MAC, with me as source now, and then marshal it on its way to the next hop. Then it stops what it was doing with the network and goes back to YouTube videos. Packets go through this linearly, like one by one, and it is very, very slow comparatively, because there's no chance of the code needed to do this IP lookup and this natting and this firewalling, etc. There's a limited chance for it to be in the CPU's instruction cache. So it always has to be loaded in from RAM And as we'll see later, we think RAM is fast, but actually in my world, it's actually very slow. So we can do this differently. One thing we can do is not have the kernel drive the network card at all, but rather use a virtual file system with user space I/O to bypass the kernel and take direct control of the network cards. So we do this by means of SRIOV or user space I/O or virtual file system I/O. But in general, the method here is all the same. We unbind the network driver in the kernel for the NIC, and we take control of it and give it to a user space process, which runs one or more threads. And a thread will run 100% CPU all the time because all it's doing is continuously pulling the network card to see if there is any packets available for it to handle in a thing called a PMD, a pull mode driver. So these PMDs are often specific to the network cards at hand. So if the silicon has some form of offloading, multiple receive queues, TCP, checksum offloading, IP fragmentation defrag, VXLAN offload, that type of stuff, it'll leverage that in the driver, but then otherwise hand off a number of packets directly for further processing. And you can run multiple threads, typically with a DPDK. One thread would receive traffic from one receive queue of the network card. And most modern network cards have, many queues, like 192 or 256 queues. So you might have as many threads taking each one section of the traffic and handling it through, and then writing it back out into as well transmit queues for the network cards. So typically you'll see the red arrows here are from the pull mode driver into one or more CPU threads running DPDK, and the green arrows are any given thread having access to all of the physical network cards using the PMD and DPDK. So real quick, how this looks like in pseudocode is you initialize DPDK with an runtime, and this runtime launches a number of these threads, and these threads are called LCore main in this case. And while we're running, all we really do is call two functions. The red one here called RTE ETH RX burst, which reads not one but a number of packets, and this is actually very important. In this case, up to 32 packets are read in one go from the network driver. And then we process them in a function called process packets, and ultimately send them back out with the RTE ETH TX burst. And again, we'll offer not one but many packets to DPDK to further schedule out. Just for reference, RAM is slow, as I said earlier. If we do a memory lookup, typically this is about 70 nanoseconds on DDR4 memory for an E5 or an E7 CPU in Intel. If we have to actually traverse NUMA to the sibling CPU, it's even slower. It could be up to 200 nanos in the worst case. But cache is much faster. This cache is memory that's in the CPU. We can read at it in 3 levels of cache, really, that get smaller but also closer to the instruction that is being executed by the cores. So L3 cache is about 10 nanos. L2 cache is an order of magnitude faster at 3.5 nanoseconds. And L1 cache, it's the fastest one we have, also relatively small in most CPUs, is at 500 picoseconds. So this picture here shows 8 megabytes of L3 cache in the center of the chip that these CPU threads that are to its left and its right are all sharing. So as soon as you can read something from the cache directly, it's going to be significantly faster, upwards of 100 times faster than you might use RAM, which we already believe is quite fast. So this is exactly what VPP does. VPP stands for Vector Packet Processing, and it uses DPDK to read not one, but a set of packets, which they call a vector. And this vector can be up to 256 packets long. And then instead of running the code for each individual packet, we run the whole vector through a directed graph, which is drawn here to the left. So all of them might come from the gray node at the top called DPDK input, and the whole list is sent to the first node called Ethernet input. And what happens now is the first packet may or may not have any of these instructions in the CPU cache. But certainly after the first packet is executed, that graph's code will be entirely in the instruction cache. So the second through 256th packet will go much, much faster because it doesn't have to touch RAM at all. And on modern CPUs, you can even use a further trick here to use the network card to write the network traffic, the packets, directly into the CPU data cache. So it won't even use memory. It'll use the PCI controllers that are already in the CPU, read from the network card directly into the D cache without touching RAM at all. This is very, very fast indeed. It's a thing called DDIO if you want to look it up. So further, the packets traverse this graph as a vector into subsequent nodes. And we use a lot of optimization with this single instruction, multiple data like SSE and AVX that essentially do one thing, but on a whole bulk of traffic at the same time. So imagine, for example, decrementing the TTL just before forwarding. You can do that on all the packets in the vector in one instruction, essentially. So we will be spending many fewer cycles per instruction that we do on the vector. Further, there's no context switches. We have huge pages, a memory construct that allows us to not use 4 kilobyte pages, but larger, like 2 megabyte or 1 gigabyte pages instead, which means we never miss TLB. It's very fast memory access as well if we do need memory. And VPP is completely lockless, which means all these threads in DPDK are running independently and are not synchronizing or waiting on each other at all. And the corollary to this is that VPP will scale linearly with the amount of CPU threads that you add to the mix. So if you can do a certain amount of packets per second on one CPU thread, if you add 10 threads, you'll have roughly 10 times that performance. Further, VPP uses a little bit of hardware offloading as well. Some of these bubbles you can imagine you could implement entirely in silicon. One popular example is QAT, the quick assist from Intel that does crypto in silicon. So these bubbles will be done by the hardware instead, alleviating the need for CPU cycles altogether. And then one last thing which I leverage, which I'll talk about next, is you can add plugins to VPP, which allow you to add code and add bubbles to the graph and rearrange the graph to add certain types of functionality. Normally, when you start this up, you run VPP and it takes control of all the network cards. So ETH0 or ENS0, these all vanish. Like you can no longer see them in the ifconfig or IP link. And instead, you can run a control binary, a CLI on VPP called Vpp Control. And you can see here that I created an interface at 10 gigabit Ethernet 300 and set it up, gave it an MTU of 9,000, gave it an IPv6 and IPv4 address, set a default route, or at least 2000/3 for IPv6, and then it started forwarding packets. And you can see how many packets it did after just a short while on the bench here. By the way, this machine is called Hippo because it's always hungry for packets. It's nice to have the data plane, but it's really important for me, at least, to be able to run higher level control plane software like BGP and OSPF in my ISP. So I wrote one of these plugins that will create TUNTAP interfaces in Linux for any given VPP interface. So TUNTAP is a driver that allows us to create a virtual device that's not backed by a physical device, but backed by a user space process. And so you might create a TUNTAP called ETH0, and it will look like a network card. It's just, it won't be physical. It will be sending its traffic to and from this user space process instead. And by doing this in VPP, if I were to receive a packet, say for an IP address that I configured on the router itself, I can copy it into this TUNTAP, which we call punting. And so if I punt it into the tap, it appears in Linux as a packet on ETH0, and I can work with that packet. For example, I might send it a ping. And then when Linux wants to send a response, what it will do is create ICMP reply and send it into this tap, which I pick up in the VPP plugin and further process as if it were a normal packet that came from VirtIO. So this allows us to do bidirectional traffic in and out of this TUNTAP for any IPv4 and IPv6, for any unicast and multicast. Further, if I make changes to VPP, I will synchronize those changes to the Linux side. For example, I set an IP address on the interface. I can copy that and apply it as well on the Linux side. And on the way back, if I were to make changes in Linux, like create a sub interface or set a route or you know, a link up or link down or MTU changes, those turn into netlink messages, which is a protocol that the kernel uses that user space processes can listen to these types of messages and act on them. And so the plugin then picks up all these netlink messages, parses them, and applies them in some sane way to the data plane. So now operators can use VPP almost exactly as if it were Linux, except much faster than the Linux kernel would. So we can configure interfaces and addresses and routes. We can do that by hand using like IP or ifconfig, or we can run higher level stuff like free range routing, FRR, or BIRD, or OpenBGPD, like as you wish. And this turns VPP into a sort of equivalent of an ASIC that runs in Linux. And these days, CPUs are very fast, as we'll see, and they're typically faster than the ASICs of 10 years ago. So for the curious, I'll not go into it in great detail here because we don't have that much time. But here are all the links to the blog posts I made while I was writing this, this plugin for VPP. Part 1 creates sub-interfaces, all types, Q and Q as well. Part 2 synchronizes the link state, MTU, IP addresses, and things. Part 3 creates sub-interfaces automatically in Linux if I were to create them in VPP. And then Part 4 does the other way around. If I create changes in Linux side, I'll pick them up with netlink and apply them to the data plane. Part 5 does that as well for routes. Routes are very intricate. We need to do them correctly because we don't want to desynchronize Linux's view of the world with VPP forwarding view of the world. And then, as we'll see in a couple of slides, Part 6 exposes all of these interface stats from VPP in SNMP, so I can add them to an NMS like LibreNMS or Observium. And then Part 7 is the practical, how do you install all of this, like compile and install it and run it for yourself on bare metal or virtual machines. I didn't write this code alone, thanks to Neil and Matt and John and a couple of others to get this in, and I'm happy to report that it will be shipping in VPP 22.06, which is slated for release in June. So now, instead of typing all those VPP commands, all I have to do is type this one command, which is VPPCTL LCP for Linux control plane create 10 gig 300 as a host interface XE0. That thing then exists in Linux, so you can manipulate it, set the link up at an MTU, set an IP address, set some IP addresses on a sub interface that I've created here called servers, which is a .1q VLAN with tag 101, give it a different MTU, set some defaults, and ping dns.google. All of this is in Linux. The only thing I would have to do with VPP is plumb through and activate this plugin so that the interfaces turn up as Linux interfaces as well. But because I can do this, and I mentioned earlier, the system handles unicast and multicast, I can now run things like OSPF and BGP. Looking at the Amsterdam router in this picture here, luckily I don't need TCAM, so memory is fine, and just with 16 or 32 gigabytes of ECC memory, I can easily hold 100 million routes in the RIB and easily hold 10 million routes in the FIB, not a problem. Because multicast works, I can as well speak OSPF and ISIS, both for IPv4 and IPv6, on point-to-points and on broadcast networks. This thing is really, really fast, though. Typically, my Junipers and Ciscos might take a minute or so, maybe 2 even, to converge a full routing table. These guys converge a full BGP routing table, IPv4 and IPv6. That's 1 million routes in about 7 seconds. But because traffic destined to the IP addresses on the router get punted into the Linux kernel, we won't see in Linux any traffic that goes through the data plane. This stuff is handled entirely in user space, and the Linux kernel is not even aware of it. So if we want to see how much traffic we did on the total machine, like on all interfaces, we have to interface with VPP in SNMP. So I wrote an agent and put it on GitHub, added the logo to LibreNMS, the thing that we use at Ibmg Networks, added some distro changes as well. The references there are the GitHub pull requests that I made. And this allows us to surface VPP, including the little doggy logo there, directly in LibreNMS as if it were a normal Linux router, except much faster. So this thing is casually forwarding 18 gigabits of traffic, and it is not even loaded. I think it's like maybe 5 or 8% total load in VPP. And this is on an Intel Xeon D, which is a 4 CPU, 8 thread, tiny embedded 10-year-old CPU at this point. But there is another really cool DPDK app, and it's called Cisco T-Rex. And Cisco T-Rex is a load tester that does stateless and stateful load testing with a Python API that you can fully control and program traffic streams on, ramp up and down that traffic, read the performance of what they call the device under test, and interact with both an API and a CLI. And because this thing is built on DPDK as well, it does about 10 to 15 million packets per core with, again, linear scaling by cores. And it has support for 1 gig, 10 gig, 25, 40, and even 100 gig Mellanox cards at line rate in both directions. Not a problem. So T-Rex is configured with basically a YAML configuration file that talks about the PCI bus slots that are used in the load tester, always in pairs. And then port info, either with source MAC addresses and destination MAC addresses, or if you want layer 3 as well, IP source and destination next hops. And really what it does is in this purple arrow on the left, it sends out traffic through this cloud, which they call the device under test, can be a switch or a router, and it expects those back on the other network card. And you can do it in 2 directions as well, so that NIC1 in the light blue is sending traffic through the DUT, and it will expect that back on NIC0. So you start this up and start a console for a CLI, and it allows you to load certain profiles in Scapy. Scapy is a packet generator in Python. You can give it source and destination IP addresses or ranges. You can give it types of traffic like sizes, packet counts, packet gaps, burst gaps, stream gaps. All of this stuff create what is called a stream, and you apply that stream to 1 or more ports, and then you configure the port to send at a certain rate, perhaps as bits per second or packets per second or percentage of line rate even. And as I said, we will expect the traffic back on the other side. Otherwise, we consider it lost in the device under test. So at IPNG, I have 2 load testing methods. The first one is to see how fast VPP can do with only 1 DPDK thread, with only 1 receive and transmit queue. So I'll send unidirectional traffic and then measure the total amount of CPU cycles that I take for, let's say, 1,000 packets per second or 1,000,000 packets per second or 10 million packets per second. And eventually this will saturate the CPU core and max out DPDK's performance for that single thread. And now I know what the single threaded performance is, which is very useful, as we'll see later. Method 2 is more like the classic RFC ramp up, where I send unidirectional or bidirectional traffic and warm up a little bit, send up linear ramp to 100% of line rate, keep it there, and expect all the traffic back. And if it does come back, great. If it doesn't come back, we can measure the point at which packet forwarding has more than 0.1% of loss and call that the maximum performance of the machine under test. So method 1 in the CLI looks like this. You start a certain traffic profile, like 1 packet replayed over and over again with only 1 port transmitting at 1,000 packets per second. We can pause, resume, update, and then eventually stop the load test. And that kind of looks like this visually. The CLI will show you this type of information here at number 1, the type of network cards that we're using and the utilization of the T-Rex CPUs themselves as they are generating and syncing the load back. Number 2 is how much traffic we're sending, both in bitrate on the line at layer 1 as well as bitrate on Ethernet in layer 2. How many packets per second as well, and what the line utilization is. And number 3 is how much we're receiving on the other side, and hopefully you receive the same stuff that you sent. And number 4 is detailed input and output packet counters and byte counters. So in this particular screenshot here, we're sending 19.1 gigabits of traffic, which is about 6.2 million packets per second of IMIX, and we're using 16% of the T-Rex load test capacity there. Method 2 is a little bit more involved, but I wrote a Python script that I published on GitHub that does this ramp up, and it will start, based on these flags at a certain low level warm up for a duration, ramp up, and keep it there. And I'll show what that looks like in a couple of slides. Sending mixes of traffic is an interesting concept in T-Rex or load testing in general. There's four that I use that get harder for the device owner test as we go along. The easiest one here is a benchmark that allows for large UDP packets to be sent with multiple source destination pairs. So at 10 gigabits, this is about 810,000 packets per second. And then IMIX, which is a mixture of small, medium, and large packets, really, that is meant to represent what a typical residential network would look like. And this is 3.2 million packets per second for a 10 gig link in one direction. And then tiny packets, the smallest ones we're allowed to send with Ethernet are 64 bytes, but we can still do them with multiple source and destination pairs, which is 14.88 million packets per second at 10 gigs. And then the last one, that's the hardest one, often for load testers, but also for silicon and software routers to do, 64 bytes, but only a constant source and destination IP port pair. So this will only be able to use one receive queue, as we'll see later. This is relevant. So then I took 3 machines, Netgate, which you may know from pfSense, also works on a thing called Tensor, which uses this code, and it has an upcoming release for the Netgate 6100, which is an Atom C3558, small 4-core CPU. Then a Supermicro, this is the ones that we use in production at Ibmg Networks. They have 6 10 gig ports and 6 1 gig ports as well. And then an ASRock Taichi with a Ryzen 5950. It's a very large CPU, a lot of threads, a lot of cache as well, which, as we saw earlier, we can leverage in Vpp quite well. So that one has 2 100 gig NICs, 4 10 gig NICs, and 4 1 gig NICs. And you'll see the price goes up, roughly doubles between the small Netgate, the medium Supermicro, and the larger ASRock. And as we'll see, the performance also doubles as well. So first method here shows the total amount of clock cycles used at 1,000 packets per second, 1 million packets per second, and 10 million packets per second. And in the top row there, you'll see the Atom starts out spending about 4,900 cycles to switch one packet if it does 1,000 packets per second. But if you ramp up the traffic, because it can use the same code to operate on multiple subsequent packets without interrupting the iCache, the total amount of cycles per packet goes down greatly, an order of magnitude or better. And then it ends up being able to saturate about 5 million packets per second with one Atom core. And note, the Atom is a tiny CPU. The Xeon D does about 10 million packets per core, and the Ryzen does 22 million packets per second per core. And it's worth noting that that's more than 10 gig Ethernet, which means any traffic we might see at 10 gigabit, even if it's full line rate at 14.8, will be able to be handled by one Ryzen CPU, and it has 32 of them. So then method 2, visually, I have a bunch of graphs following, and what it kind of looks like is the warm-up period there on the left is about 30 seconds of us sending like 1,000 packets per second just to make sure everything works. And then there is a linear ramp up from 0 to 100% of line rate and a hold duration for 30 seconds to make sure that it can sustain 100% of line rate for half a minute. And if the device doesn't handle that, it'll eventually look like this. It'll flatline and not be able to do more than, say, 35% of line rate. And if it does handle it, the graph looks like this. It just tracks to completion and ends up being at 100% for the 30-second of hold duration. That would be a passed load test. So first, let's look at the kernels. This is for pfSense, which runs FreeBSD, and for Ubuntu LTS. And if you look closely, you'll see the lines are down there. They're not very fast. Like, you can do maybe 850,000 packets, maybe 900,000 packets per second per core on the Linux kernel, and a little bit lower than that on FreeBSD, but really not much. And they're all horrible in terms of throughput. But with Vpp, everyone can be a winner. Certainly, if we do this IMIX load test, which is only 800,000 packets per second for 10 gig, all of these lines here track to completion. It doesn't matter if it's in one direction or two directions, because we kind of already know that the Atom CPU can do 5 million packets per second. So far, so good. Then for IMIX, it's 3.2 million packets per second in one direction. And if you do it in two directions, you'll see 6.4 million packets per second. And in case you were wondering, yes, all three machines will handle this just fine. And that's because the one direction is sent to one CPU thread in DPDK, and the other direction is sent to another CPU thread in DPDK, which means we can leverage two CPUs and multi-threading to do 6.4 million packets per second, even on the Atom. So we're still good. But the cracks start to show when we do 14.8 million packets per second. The Atom here, if we have one receive queue, we'll see that blue line, which is about 5 million packets per second. If we have two receive queues, we'll do a little bit more than 10 million. And if we have three receive queues at the top there, we'll see that it can saturate 15 million packets per second, but just barely. Xeon is a little bit faster. It does 10 million packets per second. And so one queue doesn't do line rate, but two queues definitely do, because you would have 20 million packets or 30 million packets per second in three queues. And the Ryzen doesn't even care, because one CPU can do 22.3 million packets per second already, can easily handle line rate with just one thread. Room to spare. Now, if we do a single flow, all the source and destination IP addresses will be the same, and we can't leverage any receive queues. So if you look under the magnifying glass there, it doesn't matter if I use one queue, two, or three, the Atom is going to top out at 5 million packets per second. And that's exactly why this 64-byte single flow load test is super relevant. And in case you were wondering, this is not just super relevant for kernel routing or the VPP-based routing, it's also relevant for silicon-based routing. If you were to use, say, link aggregation, the hardware can only choose one of the two spans to use if you only had one source-destination pair. The Xeon will do 10 million packets per second, and again, the Ryzen does full line rate, not a problem, even with 64-byte single flow. That's, of course, not all, though, because price matters. The Netgate is a very cheap machine. I think it comes in at like $700 US, and it runs 16 watt on the CPU and 19 watt fully loaded, and then it does 15 million packets per second, which is about 1.24 microjoules per switched packet. Supermicro does a little bit more, has a bigger, beefier CPU at 35 watt TDP, does about 38 million packets per second, and runs 48 watts when it's fully populated with optics, in my case, which is 1.56 microjoules. And the Ryzen, although it's a little bit more of an expensive machine, it's certainly very efficient when it does the switching, because at 15 cores, it does 330 million packets per second, just short of that. 228, I think, was what I measured. And then it uses 265 watts all up, which is 0.81 microjoules per packet. There's more to say, though, because the PCI bus is limited on the Ryzen 5950. There are only, I think, 24 lanes of PCI 4, and a typical dual 100 gig network card will be PCI 4 16 lanes already, and so there will be only 4 left over, for other network cards to use, and typically will bottleneck way before the CPU runs out, right? So the real bottleneck here on this Tai Chi with the Ryzen isn't actually the CPU, it's going to be the PCI bus, which is going to allow us for roughly 700, maybe 750 gigabits of traffic all up. Still not bad for a $3,000 router. And then in the remaining 10 minutes I have before I have to sign off, I'm going to give a couple of demos, not really demos, but screenshots of configurations that I think are really cool that you can do with VPP. Again, fully open source and very, very fast performance-wise. To the left here is the rack that I test this stuff in. So first, let's look at a layer 2 cross connect, where in Vpp Control, I'll set up this 100 gigabit Ethernet 12.0.0 and 0.1 up, set the MTU to 1500 bytes, and then do what is called an L2 cross connect, which connects these two back to back together in the data plane, which means every packet I ever received on 100 gig 12.0.0 will be immediately sent out on 12.0.1 and vice versa. You can do anything on this Ethernet pipe. It looks like a long Ethernet cable, and those of you that use L2 VPNs, virtual lease lines, and Ethernet over MPLS will see a very, very similar feature set here. And we can also do this with sub-interfaces, though. They don't have to be only Ethernet interfaces. For example, we'll create these two interfaces and then create a QIN AD sub-interface here called 1201.10, and we'll give it a .AD100 tag and an inner .1Q200 tag. Create that, and then use tag rewriting to remove those tags on received packets. So I'll just see again the Ethernet frame without the tags, and then on transmit set the two tags back. And then I'll create a .1Q regular VLAN interface 1234, call it subinterface 11 on the left-hand side, and then pop only one tag because it carries only one tag, and then cross-connect these two together. Of course, I can still use any other sub-interfaces on 100 Ether, 1200 or 1201, not a problem. Like, these are all still available. So demo 3 here is, let's take this 100 gigabit Ethernet card 1300 and bring it up and give it 9,000 bytes of MTU. Let's take 1201 and give it an IPv6 address and bring it up at 9100 bytes. Speaker notes in my slides say why this is 9100. Then create a VXLAN tunnel interface called VXLAN tunnel 0 from the source to destination with a VNI of 8298. Set it up and give it an MTU of 9,000. And cross-connect the two. So now we have a virtual lease line with a VXLAN underlay without any learning or any sort of MAC address shenanigans. And as we'll see, it's very, very quick. You can also create just a .1Q interface with VLAN tag 55, create maybe a Geneve tunnel instead with IPv4 underlay, and then cross-connect those two together as well. We can do this at the same time, you know, of course, and Geneve as well as VXLAN have silicon offloading in most modern network cards, certainly the Intels that I use in my ISP. So what it looks like performance-wise, lower is better. Here's a graph that shows how many CPU cycles the machine has to spend in VPP to switch one packet. And it's about 150 CPU cycles to switch a packet just with layer 2 cross connect, which means that I can still do 15 million packets per second on L2 cross connect. And then GRE VXLAN Geneve with IPv4 and IPv6, which get more expensive over time. But when I say more expensive, I still mean the slowest one here can do about 8.5 million packets per second on one CPU thread, doing the tunnel NCAP and DCAP at the same time. My screen is dropped. I'm not sure if I still have video. All right, then I'll just continue as if. So we can do bridge domains as well. These are normal bridges. I'll create a bridge domain with number 10 and put gigabit Ethernet 10.0.0 in it. I can, of course, add a IP address to that. It's called a BVI in Cisco language, a bridge virtual interface. Give it a MAC address, give it an IPv4 and IPv6 address, and set it up into the bridge. So now gigabit Ethernet 10.0.0 machines behind it can ping, of course, this IP address. I can then create with LCP a host interface BVI 10 in Linux that carries those IP addresses, and I can, of course, speak anything I'd like over that, OSPF and BGP and all of that stuff. I can add a bond interface with a lag. In this case, it's LACP signaled with an L2 load balance strategy. Maybe add two 10 gig ports to it and bind them into the bond Ethernet, and then add that bond Ethernet to the bridge. And so now gig 10.0.0 and the bond 0 will see each other, and of course the BVI as well. And to finish it up, I can as well add those two tunnels that I created earlier and have remote ports on machines that participate in the same layer 2 domain with that bond, and as well as that 10 gigabit Ethernet 10 port. So that's what I had for you. Luckily, because it's a little bit annoying that I don't see the Zoom call anymore. Thanks a lot for your attention. If there's any questions, we still have some time left. If you don't peer with ASA 298 and you could in Frankfurt, Amsterdam, or maybe Zurich, please do. It helps us a lot to test and further develop the control plane. I have links to FIDO website for VPP, as well as my code for the Linux control plane itself, and a whole set of articles on my website that describe a little bit more in-depth details on how this stuff is all meant to work. And if you can follow me on Twitter, that would be great. Thanks a lot for listening, and now back to the studio for